Okay, so I'm going to be talking about nonlinear perturbation theory and the galaxy bispectrum. So first I'm going to walk through nonlinear perturbation theory for the matter density evolution, and then we'll apply these corrections to the power spectrum. In the second half of the talk, we'll go through the galaxy matter bispectrum, and we'll then take a look at some of the current observations of galaxy bispectrum and their results, and finally finish by discussing future plans and challenges for the galaxy bispectrum. So we start off with the Boltzmann equation, and this is this equation that governs all of the stuff in the universe. So it's a differential equation that gives us df dt, where f is the distribution function. Remember that the distribution function is the number of particles in a given volume in phase space. And if we scale it up to a whole ensemble of particles, it gives us all of the macroscopic properties of the entire ensemble. So in relativity, we use the stress energy tensor, and we can go from this distribution function f to get the stress energy tensor T mu nu. The Boltzmann equation is effectively a conservation equation, and it can be broken down into two different equations, the continuity equation and Euler equation, which give us the conservation of mass and the conservation of momentum for a fluid. The latter is effectively like Newton's second law for a fluid. So the second equation that we need is the Einstein equation. And this connects all of the stuff in the universe in the form of the stress energy tensor to gravity. And the stress energy tensor is what connects the Boltzmann and Einstein equations. So previously we assumed that we had some small density and metric perturbations, delta and psi. And by small, we mean that they were to first order, so they were linear. And this turned the Einstein equation into the Poisson equation. And then we solved the resulting linear Poisson equation and the fluid equations for the matter evolution. Now, the problem with that is that on very small scales, matter becomes very dense. So the density perturbations delta become very nonlinear. And so the linear approximation become very poor on small scales. So to correct for this, we need to take the nonlinear forms of these equations, of the Boltzmann and the Einstein equations, and then solve them for the delta perturbations in the general case. So we start off by taking the Boltzmann equation. We put some non-relativistic matter in it, and also the geodesic equation, and that gives us the Vlasov equation. And this equation holds for arbitrary size perturbations. So we're not making any assumptions that we have small perturbations. The good news is that the space-time perturbations psi are actually still small on all scales. And so we can continue using the linear Poisson equation for that. So it's only the density perturbations where the linear approximation starts to break down. And since we're working on small scales, we can use Newtonian gravity. Now the Vlasov equation gives us the distribution function f and psi, or it's in terms of f and psi at least. And the Poisson equation is in terms of the overdensity delta and psi. And delta, as we'll see in the next slide, is just an integral over f. And so because of this, this Vlasov-Poisson system is called a coupled nonlinear integral differential equation in 6+1 dimensions. So that's all to say this is a very complicated system to solve. So to solve it with the perturbation theory, we're going to take moments of the Vlasov equation. So by moments, I mean integrals over momentum. And this is analogous to the first and second moments in statistics. So the first moment being, for instance, of a function f of x, we multiply by x and we integrate over x. So here we do the same thing, but with momentum. So when we take the zeroth momentum of the Vlasov equation, that's just an integral over all momentum. This ends up taking the zeroth moment of the distribution function f. And by definition, that's just the number density, which we can easily turn into the matter density delta. And so this zeroth momentum Vlasov equation, the zeroth moment of the Vlasov equation becomes the continuity equation. And then we can take the first moment of the Vlasov equation, and that gives us the Euler equation. And it also gives us the first moment of the distribution function, which is just the fluid or bulk velocity u. So taking these moments integrates out the momentum, so it reduces us from a 7-dimensional problem back to our usual 4 space-time dimensions. And it turns our f's into deltas and u's. So we get the same Euler-Poisson system as before of 3 equations, and now we have 3 unknowns to solve for. It's the delta one that we're interested in. And so we'll assume a solution for delta, and that is that it has this form here. And when we look at the equations, we start to see that this actually makes a bit of sense. So this is saying that the general over-density perturbation is equal to our first order linear approximation solution plus higher order correction terms. And each term is smaller than the last, and it depends on the last term. So this is what happens when you put this zeroth order solution, first order solution into the equations. We see that we can start to iterate to get these higher order terms. And so what that means is they all end up depending on our linear solution. So we can write all of these higher order corrections in terms of just our linear solution. So looking at just the second order solution in Fourier space, what that gives us is our first order linear solution, which is our delta 0 times d plus, which is our growth factor. And so remember, delta 0 is just some perturbation at some time, and then you hit it with this growth factor, and that changes it over time. So we have 2 first order solutions here, both evaluated at different k's. We multiply it by this f2 polynomial, and then we integrate the whole thing over these k spaces, k1 and k2. And so it's a little bit easier to see, I think, with these kind of tree schematics. So the second order density perturbation, delta 2, depends on 2 delta 1s, each evaluated at a different k, and you just multiply them together along with this f2 polynomial, as well as the appropriate factors of 2 pi and a delta function, and that gives us our second order correction. Now we can also do this with the nth order correction. We just take n number of linear solutions, multiply them by this f sub n, and the appropriate 2 pi's and a delta function. Now this f sub n depends on all of the input k's from the linear solutions. And so an nth correction has this n number of arguments k here. And all of these polynomials are actually pretty easily computed because there's this recurrence relation, so they all will depend upon previous values. So these f's, these polynomials, are called interaction kernels. And their primary job is to introduce something rather different from our linear solutions, and that's mode coupling. So that is, their arguments uh, are different modes, different k values, and the polynomials themselves depend upon combinations of these, or its particular dot products between these k's. And so they couple these modes together. And this is one of the biggest differences between linear and nonlinear theories. So what's shown here is the F2 kernel for an Einstein de Sitter universe, so mega matter only, no dark energy. And here we have these three terms. And each of these terms corresponds to a physical effect that's causing this mode coupling. So the first term here is refers to the growth of the nonlinear perturbations, or the nonlinear growth of the perturbations. The second term here is called a shift term, and this encodes in it all of the motion of the density perturbations from the gravitational potential from other perturbations. So it's the effect that other perturbations have on a given perturbation gravitationally. And then this third term here talks about, or gives you the distortion of the perturbations in this anisotropic manner. So this is called the anisotropic term. So we can apply this nonlinear density perturbations to get a nonlinear matter power spectrum. So we start off by multiplying our deltas together and averaging them. That's just, by definition of the power spectrum. So this first term here is just our linear matter power spectrum. And then we have these two other terms. And we can rewrite this in terms of the power spectrum here. So this first term is the linear power spectrum, P sub L. And then we have P22 and P13. And those correspond to these terms here. So P22 corresponds to the power spectrum between two second order density corrections. And then P13 is the power spectrum between the linear and third order term. And these actual power spectra are given here, but again, it's easier, I think, to see this in the tree schematic. So here we have two second order corrections. So we have two trees. And the effect of taking the power spectrum between these two is that their roots, if you want to think of them as these linear deltas here, are coupled. And they're coupled. By coupled, I mean they form a power spectrum between them. Right. So this is the linear power spectrum times, again, a delta function and some factors of 2 pi. So you have two linear power spectra because there are two of these pairs of linear deltas. And so they combine in this way, and then they get hit by these two kernels, and that gives us this P22 equation. Now here, these p's, these little p's in this equation, are just shorthand for all of the k's that we're integrating over. And they depend, their arguments of the linear power spectra depend on each other in this kind of way. And when this happens, and when you integrate over all of p, this is called a convolution. So, and then again, we can hit them with this F2 kernel. And we can do the same kind of analysis for the 1 and 3. Right, so here we have this just one tree here, and then we have a third order tree. So it has three linear terms. And so we convolve them, we take their power spectrum like this, and that means that the final delta corrections are convolved in this way. So the main takeaway here is just that you can calculate these higher order corrections to the power spectra pretty easily over these integrals. And all of these integrals are just over this polynomial and the linear matter power spectrum. And when you go out to include just these extra terms, this is called the next leading order, or NLO, matter power spectrum. Okay, so here we can actually see the effect of these nonlinear corrections. So at z equals 0, we have the solid line here being the linear power spectrum and the dashed line being the nonlinear power spectrum. And we see that they start to diverge at about 0.09, a k of 0.09 h per megaparsec. So we see that that's right after the first bow wiggle. Oh, sorry, the baryon acoustic oscillation wiggle. And so we can see that the effect of including these nonlinear terms is to smooth out these bow features. And here on the bottom, we just have this ratio between the nonlinear terms and the linear term. And so as it starts to get higher and higher on the bottom here, that means that the linear corrections are starting to get of the same magnitude as the nonlinear corrections. And so once they finally hit 1, so once they're about equal to each other, that's when our nonlinear theory begins to break down. And what we can see here is that at higher redshifts, the linear theory holds for a little bit longer in K, so for smaller scales before it kind of starts to break down. And so we can see a bit more of the bow feature. And we expect that, right? Because at higher redshifts, we're essentially looking back in time, and we expect the perturbations to be smaller then. So the linear approximation becomes better and better. So in the linear regime, the power spectrum, or the 2-point correlation function, contains all of the statistical information of the field. And what that means is that the odd numbered correlation functions are all just 0, and the even ones can all just be written in terms of the 2-point correlation function. But once you introduce nonlinearity, the information starts to move from the power spectrum into the higher order statistics. And so the next one statistic to look at is the 3-point correlation function and its Fourier transform, which is the bispectrum. And here we have that written out explicitly, completely analogously to the power spectrum. Here we have just multiplying these deltas in k-space and averaging them gives us the bispectrum, along with this delta function and the appropriate factors of 2 pi. Now, this bispectrum is actually pretty useful, as we'll see, and can actually be even at times better statistic than the power spectrum for the purpose of cosmology at nonlinear scales. Now, the introduction also of this third k in the delta function means that all of these k's need to vectorially add up to 0, essentially. So what that means is all of these k's need to form closed triangles. And so depending on what the lengths of the k's here are, they will form different shapes for these triangles in k-space. And we refer to that as the bispectrum's shape. So when measuring it, you can think of it as going into k-space and creating a bunch of these triangles and adding them all up. Is one way of thinking about calculating the bispectrum. And the bispectrum shape is usually how we differentiate between different models for the bispectrum. So the first shape we'll be talking about is the tree level bispectrum. So here its shape just comes from the kernel and the power spectrum. So by tree level, we use our tree method from earlier, just like with the power spectrum, to calculate the bispectrum. So again, we have that the bispectrum depends only on the linear power spectrum, and they're added and mixed together in these special ways, and they all have these kernels. And these kernels for the bispectrum are the same, exactly the same kernels that we had just shown for the power spectrum. So if you use that formalism, then the resulting bispectrum is called the tree level bispectrum. And this holds for large scales or small perturbations. But we can also extend this actually to larger scales as well. And so there are a couple of ways of doing this. For one, we can correct our kernels or make better kernels essentially by adding in some free parameters and then varying those free parameters and compare them to sims to get kernels that fit the data at smaller perturbations a bit better. Smaller scales a bit better. Another way of doing it is by taking, instead of the linear power spectrum, by using the nonlinear power spectrum in these calculations. And often both are actually used. So that was the matter bispectrum. The galaxy bispectrum is a bit more complicated. So again, here we have this term, which is actually analogous to, or actually almost completely identical to the bispectrum case for matter. So we have this F2 kernel multiplying by these linear power spectra. And we also have like two other terms here that are just different permutations of the case. And that would be the matter bispectrum. But for the galaxy bispectrum, we have something called a bias. So what that is the ratio between the galaxy densities and the matter densities. And so when you introduce this bias, it has the effect of changing the kernel that we use. So we have to use a special galaxy kernel. And we add this extra noise term to the bispectrum, B sub n. And this bias is also kind of complicated and nonlinear. And so it really complicates things. Some other shapes include the squeezed or local shape, and that's where you take K1 and K2 to be about equal, and they're much, much greater than the third K3. And what this does is it couples these large scales, which correspond to the tiny k, and the small scales, which correspond to these large k. Other shapes include equilateral or constant shapes. So this is where you take equilateral triangles, so K1 equals K2 equals K3. And you can also use isosceles triangles. So an example of actually calculating the bispectrum here was done in this 2015 paper by the Sloan Digital Sky Survey's BOSS survey, which is the Baryon Oscillation Spectroscopic Survey. And so in their 11th data release, they released this analysis of a little under 700,000 galaxies that they surveyed with this between the redshift of 0.43 and 0.7. And what they saw was with their bispectrum that they calculated, which actually we can just show right now, here they made all of these calculations of the bispectra. So this top row here is or are values of the bispectrum for K1 equals K2. So this isosceles triangle. And the bottom row here all has K1 equaling half of K2. And then they're just plotted out as a function of K3 at these different K1s. So it's a little, the reason why we have so many different plots here is because this thing is, this bispectrum is fundamentally, a function of 3Ks. And so you can take different slices through K space and you get different plots here. And the red and the blues just correspond to their two different data sets. So one use of the bispectrum in terms of actual science is it's able to break the degeneracy between this galaxy bias and sigma 8. And in this case, this was done by adding in these extra bias factors in the bispectrum. So as we saw previously in the galaxy bispectrum, you have not only this one bias factor, but you have multiple bias factors here. And normally, if you're working in the linear regime, like in the linear power spectrum, you only have one bias factor. And so that causes a bit of a degeneracy with sigma 8. But when you add in these extra bias factors and fit the data as the model to the data, then we can constrain just the bias factors separately from sigma 8. And this was done by using both the power spectrum and the bispectrum. It was also rather impressive because it was able to calculate the rate of the growth of structure, so the dn, dA essentially, where A is the scale factor, from only clustering data, which is the first time that's ever happened. And the specifics of the bispectrum they used was essentially this tree level bispectrum with the improvements that I had mentioned earlier. The downside is that this model is not very good for the squeezed configurations of the bispectrum. So up until now, that what I just talked about with constraining the bias, that was used by just fitting the bispectrum to the data and seeing how well it fit for different values of the parameters. But what's really cool about bispectra is, as well as the power spectra as well, is that it can also be used as a standard ruler. And so this can be used to set cosmic distance scales. So that is line up redshift with an actual distance. So the way that this is done is we assume that the distance, the difference in the distances that we might have, some error in the distance, just scales the spectra that we're interested in. So all we need to do is plot out the spectrum and adjust the distance around a bit until we get a good fit to the data. And that distance would then correspond to that redshift for the data. Now, one example of using the 3-point or the bispectrum as a standard ruler was done in the BOSS's 12th data release. And in this case, they use the bow feature in the bispectrum. So this BOSS data release was the largest and highest signal to noise galaxy bispectrum survey to date. And what they found was, analyzing that data, was they found that the bow actually did have an impact in the bispectrum. And this is the first really strong detection of, up until about 4.5 sigma, of bow in the bispectrum. So using this, they were able to put a very tight constraint down to the percent level on the distance redshift relationship. And they also managed to put on one of the tightest constraints on the linear bias using the bow feature in the bispectrum. And then also using the bispectrum, they were able to put the tightest constraints on early baryon dark matter relative velocities, which is important because these early relative velocities between baryon and dark matter right after the decoupling, so right after the bow is formed or so, any uncertainties in that velocity can change the number of galaxies that end up forming, and that will mess up the actual measured distance redshift relationship. And the uncertainty here in the velocity is a very important systematic in cluster, especially future cluster analyses like DESI, because they rely very heavily on this accurate distance redshift relations. So some future surveys that can take advantage of the bispectrum, or that the bispectrum analyses can take advantage of, would be large galaxy surveys like LSST, DESI, and Euclid. DESI in particular is very good for the standard ruler approach because it's a spectroscopic survey as well, or primarily. And so you can get these very good accurate redshifts. So it's good for constraining cosmic distances. And in general, the sheer amount of data we'd be getting in these three-dimensional galaxy surveys would be much greater than the two-dimensional data sets from stuff like the CMB, which is one of the reasons why the bispectrum is an increasingly popular statistic to look at, as opposed to, say, the power spectrum of stuff like the CMB. So just quickly, some problems going forward, or some difficulties, is this nonlinear bias that I had mentioned. It is quite complicated. And so the higher order corrections to certain bispectral shapes, like the equilateral shape, is not actually worked out because adding in this nonlinear bias, it complicates the math by quite a bit. And in general, trying to get a handle on this bias is pretty difficult because, from a theoretical point of view, because baryonic astrophysics is quite hard and it messes with our cluster measurements. So other problems can include uncertainties in the average number of galaxies. And that's important because that is what gives us our deltas that the bispectra will eventually depend on. Another problem is galactic extinction, particularly on these very large scales. And in particular, it's very important for stuff like primordial non-Gaussianities measurements. And finally, the distances to galaxies are really important to figure out because the bispectrum can depend very sensitively on them. Right, and there's a bunch of other cosmology you can get out of the bispectrum. There's a whole subfield growing of primordial non-Gaussianity constraints from bispectra, which when you include it with the power spectrum can get you significantly better constraints. Can also get stuff like an effective neutrino mass from there, constrain other cosmological parameters with the bow feature in the bispectrum that I hadn't gotten to, and it also can be used for testing modified gravity theories. Okay, and that's about it, and I'm way over time. I really apologize for that. I don't know how to stop this thing.